I'm feeling in a mood for maybe another couple of problems, depending on how it goes, from the chapter called The Invariance Principle from this book on problem-solving strategies. I hope it'll go a bit better, or a bit more quickly than the last one where I got stuck on a problem, but we shall see. So let me share my screen and tell you what the next problem on the list is. So it's question 9. It says each of the numbers from 1 up to 1,000,000, which they call 10 to the 6, is repeatedly replaced by its digital sum, which I presume just means the same as sum of its digits, until we reach ten to the 6 one-digit numbers. What on earth is the question going to be? Will these have more ones or twos? I'm confused. That looks as though it's going to be either I misunderstood the question or it's just boring. Because we know that if we replace a number by the sum of its digits, it remains the same mod 9. So is this not simply asking whether there are more ones or twos? Mod 9, I think that is. I think this is just a sort of appropriate enough for question 9. Obviously, it's going to be at least as many ones as twos because we start with a 1. So basically, every number n will remain constant mod 9 when we replace it by the sum of its digits. And when we get down to one-digit numbers, until we reach one-digit numbers, so we won't reach 0, we'll reach 9. So we'll reach a number from an integer from 1 to 9, and it starts at 1. And we go all the way up to 999,999 is 0 mod 9, so 10 to the 6 is 1 mod 9, so there'll be 1 more 1 than 2. Answer, ones. Don't even have to write anything. So let's move on to another question. I don't count that as going well because there wasn't really much to it. So question 10. The vertices of an n-gon are labelled by real numbers x1 up to xn. So we have x1, who knows why they are going around in an n-gon, but we'll come to that, I suppose. Let A, B, C, D be 4 successive labels. Help, this is looking scary. I've just seen the next thing. If A minus D, B minus C is less than 0, then we may switch B with C. Did I get that right? Yes, B with C. Decide. Okay, it's not quite as scary as I thought. I'll explain why. So decide if this switching operation can be performed infinitely often. Well, I'm pretty sure the answer is going to be no. But so why I was scared was that we had this sort of algebraic expression A minus D times B minus C, but now I see it's just a sort of silly way of saying if A and D, the sort of comparison between A and D is different, strictly different from the comparison between B and C. Did it say they're different real numbers? No, it didn't, but so if A is greater than D and B is less than C, or if A is less than D and B is greater than C, then we're allowed to do the switch. So we had something like 3, 5, 7, 2 going successively round, we'd be allowed to change that to 3, 7, 5, 2. Because that would mean that now the comparison between 7 and 5 was the same as the comparison between 5 and 2. So we are probably looking for some number that goes down. I'm presuming that the answer is going to be no, that no, it can't be done infinitely often. But I don't immediately see what number I want to choose here. It might be something to do with the number of pairs that are the number of pairs xi plus 1, where xi plus 1 is greater than xi. Perhaps that always, it's hard to know quite what's going to happen there. So, or maybe it would in fact be some parameter associated with A, B, C, and D, which I would sort of keep summing, but then there would be other collections of 4 successive things, and I'd have to check that the parameters associated. Maybe there's some sort of big algebraic expression I could write down and prove that it goes down, but I don't see that just yet, so I feel I need to look at an example. And I want to look at a fairly simple example. Something like that. I mean, it's simple in the sense of easy to describe. So it also seems like a reasonable candidate for something that where you could do it infinitely often, if it is in fact ever possible to do it infinitely often. So this 7, 3 is going in the opposite direction from 1, 2. 7 is bigger than 3, but 1 is smaller than 2. So I can swap 1 and 2. Let's just do that and see what happens. Now 2, 4 is going in the same way as 1, 3. 1, 5 in the same way as 3, 4. 3, 6 in the same way as 4, 5. But 6, 1 and 7, 2 are going in the same direction. 7, 3 and 2, 1 are going in the same direction. That came as a bit of a surprise to me. So here's an example then where you can't make a move. Unless I've missed one, but I'm pretty sure I've checked all of them. How did that work though? And can we somehow see what's going on? So one observation here is that it's going up and then it's coming down, but it was all actually, even before I did that, it was going up and coming down, but it just came down rather abruptly from 7 to 1. And now we've got the 7 to 2 to 1. 6, 1, 7, 3 to 1. Okay, so let's just quickly ask the following question. Supposing we go from we increase A1, A2, A3 up to AK, so that's always going bigger, and then from AK onwards it gets smaller again. AK plus 1, AK plus 2, up to AL, and then down to A1. So A1 is the smallest, increases up here, AK is the biggest, decreases in that direction. Can we, so AL, so A1 is smaller than A2, so it actually depends whether AL is smaller than A3 or bigger than A3. So we can't say anything about this very general situation. We'll have a symmetrical situation down here. But if AL were to be, supposing we were able to make a change, so if AL is bigger than A3, then we go from A2 to A1, and then we can't make that change anymore. and A2 is smaller than A4, A1 is smaller than A3. So now we're sort of stuck here. What about over this side? A1, A2. So if AL minus 1 that was if AL was bigger than A3, so also AL is bigger than A2. So if AL minus 1 is smaller than A1, but it's not smaller than A1. So we don't have much room to make changes around here. So I'm getting a sort of, maybe another thing I want to look at just before I go any further. I suppose it would be possible for the sequence to sort of go up and down a few times, because we could just take one of these things and duplicate it. So I go, if I've got something where I can't make a move, then I duplicate it. 1, 3, 4, 5, 6, 7, 2, 1, 3, 4, 5, 6, 7, 2, and make a sort of circle double the size. Then obviously I still won't be able to make a move. So it's certainly not going to be the case that you've got to get stuck at a configuration like that. So this is I'm starting to enjoy this question, even though I don't see my way to a solution just yet. And now I have just a sort of wild guess, actually. Which is, sums of squares are sort of fun things. What happens, let's just go back to an example 3572. So the differences here are 2, 2, and 5. And if I change it to 3752, what happens to the differences? They become 4, 2, and 3. So those two add as 1, that adds up to 9. And that interestingly adds up to 9. And was that necessary? So the middle difference is going to stay the same. But what about the outer two differences? I better do this in generality. So A, B, C, and D. All I know here is I'm going to assume that A is less than, or A is greater than D, let's say, and B is less than C. And then the question partly is going to be how much am I going to have to do lots of cases according to whether B is bigger than A or smaller than A, and whether B and C sort of lie. That's slightly irritating. But maybe I don't care whether the sum of the differences remains the same, because I feel it's going to be more promising to look at the sum of the squares of the differences, and this was the wild guess. So does it go down in this instance, first of all? So here we have, it looks as though it does, because this looks a bit more sort of spiky at 5. But let's just think about that. It's 4 plus 4 plus 25. So that's 33. And here we have 16 plus 4 plus 9, which is 29. So there's something that might work. So let's have a look. We have a minus b squared plus b minus c squared plus c minus d squared. And a nice aspect of that is that we don't, oh, sorry, I was going to say we don't affect, yes, we don't affect d minus e squared. So if we just look at the sum of the squares of the differences all the way around, we can sort of isolate the effect in a nice way. But is this going to go down when I swap b and c? What's that compared with? It's compared with a minus c squared plus b minus c squared plus b minus d squared. And, well, that's looking promising, because those two obviously I don't have to think about. So let's think more carefully what we have to compare with. So the a squared we'll have, up here we'll have, I'm forgetting about the b minus c squared, so we're going to have an a squared, a b squared, a c squared, and a d squared. And here we're going to have an a squared, a c squared, and a b squared, and a d squared. So the only question is whether, so this is sort of number 1, and this was before the swap, and that's after the swap. So the 1 is going to be on the left-hand side. The only question is whether minus 2ab, I'm hoping this is going to go down, so I want minus 2ab minus 2cd to be greater than minus 2ac minus 2bd, which is the same as wanting ab plus cd to be smaller than ac plus bd. And this is looking familiar. I think this is going to work, but so I know that if you want to maximize an inner product, this is just a fact that I know, but we can check it anyway. Oh, well, let me just check this in this instance, and then I'll talk about the fact that I knew it. So let's just simply subtract this side from this side, and we get we see that it factorizes. We'll get a times c minus b minus d times c minus b, which is of course something that I was rather hoping we'd get. A minus d, what did I just say, times c minus b. So we want, in order for the comparison to go the right way, we want that to be greater than 0. And that looks awfully reminiscent of what we were told. A minus d, b minus c less than 0. Which is, okay, so that's exactly the same. If I swap b and c around, I'll get that that's less than 0. So I seem to have solved this problem. But let me just quickly make the remark that I was going to make about two sequences. So supposing I've got sequences a1 up to an and b1 up to bn of, let's say, non-negative real numbers, and I want to minimize the inner product sigma ai b pi I over all permutations pi. So I'm allowed to sort of change the order of the coordinates b1 up to bn, and I want to minimize this inner product. Then the way to do it, I could say without loss of generality, the a1s are decreasing, so let's actually just assume that. So let's assume that a1 greater than or equal to an greater than or equal to 0. The way to do it is to choose the permutation pi in such a way that b of pi 1 is greater than or equal to b of pi I greater than or equal to 0 as well. And the way you can check that is that if ever you've got two things that are not in the same order, you do better by switching the b's. That's a simple verification to make. So that was a fact that I knew, but then this is a special case when n equals 2. So I feel good about that in one way, which is it's always nice to solve a problem reasonably quickly. Less good about it in another way, in that I solved it by making a bit of a guess that, but maybe if I come back and watch this, I'll be able to understand a little bit about why it was a natural guess to make. But it felt a little bit like the sort of flash of inspiration that I want to argue is never necessary, or not sort of genuinely necessary. Right, next question, and I think I'll stop after this one. Well, I suppose I've only done one real question because the first one was a bit ridiculous. Excuse me while I just draw this. So in figure 1.5, which has 1s everywhere except there's a -1 there. Right, what can you do in this figure? You may switch the signs of all numbers of a row or a column or a parallel to one of the diagonals. So switch in row, column, or parallel to diagonal. Now, it's not immediately clear what parallel to diagonal is, but luckily the question contains a clarification. It says, in particular, you may switch the sign of each corner square. So I'm taking it that that means a parallel to a diagonal is simply something like, these two would count as being parallel to this diagonal. You would not have to do a sort of mod 4 diagonal. You don't go 1, 1, 1, 1. And so in particular, if I take a diagonal line that just goes through this square, that means I'm allowed to change this -1 and similarly. So I'm allowed to change that, or those two, or those three, or those four, or those three, or those two, or that one, and similarly on the other side. What's the final question? Prove, well, the way the question is worded, prove that at least 1 minus 1 will remain in the table. I think I prefer to say prove that there will always be at least 1 minus 1. Okay, I think I've just sort of accidentally, I'm not sure, but I've just had a very quick thought that I think may have instantly solved the problem. But we'll see about that, because I could easily be wrong. But in fact, I don't think it does work. So so our first observation is that we can't just look at the parity of the number of -1s because we're allowed to change a corner. So the next thought one might have is, well, what about, this was the sort of thought I was having, perhaps we just say, we'll write off the corners. We're not going to be able to say anything about them. So since we can't say anything about them, there's no point in even thinking about them. We might as well just have the figure that looks like this. Because unless we can prove that there's always going to be, if we can't prove there's going to be a -1 inside here, then we're doomed, because we can't rely on there being a -1 in the corners, because we can always change the signs in the corners. But now it looks as though a parity argument might be possible, because I take that back. So we have 3 things here, so we don't have a parity argument. But then I'm now wondering whether we can nevertheless find some subset that contains this, such that we can still do a parity argument if I just look at that subset. And I think I possibly can. If I ignore the 4 central squares, then all horizontal lines we're going to cross it in an even number of things, all vertical lines in an even number, and the diagonals now cross in 2 and 2 and 2 and 2. So just to repeat what I'm doing, I'm erasing the middle here and just saying that the total number of 1s in those 8 squares is going, sorry, total number of -1s is going to have its parity preserved, because, well, I've just verified it, just everything that intersects those 8 in an even number of squares. That's it. So parity did work. I think I won't write that down. But actually this is a special case of a very general parity type argument, so I might just quickly mention that. So what we would like, we can look at it like this. We would like to have some kind of mod 2 linear, a sort of map from this to F2 that is going to remain constant. It'll be our invariant. And if it's going to remain invariant, we can just see by looking at this 1 here that, so what we're effectively trying to do is to find a vector generated, so I think of each one of these squares as being a sort of standard basis vector. I can put either 1 or -1, which in mod 2 is like saying 0 or 1. And I want to find a vector that is orthogonal to all the vectors that you get from these rows, columns, and diagonal parallels. So it's got to be orthogonal to this one, it's got to be orthogonal to that, it's got to be orthogonal to that, and so on. So it's sort of, in a sense, you're solving some kind of system of, well, you're solving a system of linear equations over F2, and it just happens that the vector that's 1, 1, 1, 1, 1, 1, 1, 1 is indeed orthogonal mod 2 to all the relevant vectors. So if I hadn't sort of had a flash, hadn't had a sort of brainwave, so to speak, it wasn't really much of a brainwave, but I hadn't had the idea that I could just look at the characteristic function of those 8 squares, I could have actually worked it out by doing a bit of simple linear algebra over F2. There's that little remark. Since that also was quite quick, maybe I'll allow myself one more question. I'm sort of tempting fate by continually allowing myself one more question. So that might be the question that jumps up and bites me, but never mind. So we're on to question 12. Let me just get rid of this. I'll leave it there. There's a row of 1,000 integers. I quite like these random large numbers that the questions have. There is a second row below. This is starting to sound a bit scary, like the one that caught me out, but never mind. Which is constructed as follows. Oh, that's looking better. Under each number A of the first row, there is a positive integer such that FA equals number of occurrences. Okay. Of A in first row. What do we have to prove? In the same way, to reiterate this operation, not surprisingly, we get third row from second, and so on. I suppose it's going to say prove that it terminates. No, yeah, well, sort of saying prove that finally, or I'm going to say eventually, one of the rows is equal to the next. So in other words, this iteration is eventually constant. So this again looks as though so I'm getting a bit too much sun in my eyes. So looks as though we would like to find some quantity that decreases, but what might that be? I think it's always a question when you're looking at a problem like this. Should one try to sort of think very theoretically and try to avoid playing around, or should one play around and just let that help you come up with ideas? As I think the videos have shown, I've tended to have a sort of habit of doing quite a bit of playing around in order to get the thoughts to arise. Not always, but often. And here I'm sort of looking at this problem and feeling as though I don't quite see how I'm supposed to guess what quantity might decrease. So just to get a little bit of a feel of it, I don't think I'm going to have to. So just to try a couple of examples. So if I tried something like 1, 2, 3, 4, 5, then I'm just going to get 1, 1, 1, 1, 1. Then after that I'll get 5, 5, 5, 5, 5. Okay, so that already shows me something useful. I'm not going to get something like that the sum of squares goes down. Not that I was expecting that, but there's a rather clear thing. The sum of squares clearly goes down and then leaps up again. But perhaps if I were to look at the number, what do I have here? I have the number of ones, number of twos, number of threes, number of fours, number of fives. So if I look at the numbers of different things, I've got some 5 numbers that add up to 5. So initially it's 1 plus 1 plus 1 plus 1 plus 1. Then in the next time, it's 5 plus 0. So I've got 5 ones and none of anything else. And in the next one, it's 5 plus 0 as well. And it seems at least possible that it's always going to add up to 5, but here now we might be able to say that the sum of squares increases. So the sum of, because here it's rather sort of spread out, and then it's ended up being much more concentrated. So what am I trying to say? So supposing I've got, let's try to write something down that's rather sort of abstract. So in fact, no, what I'm going to do is I don't actually care what these numbers are, I think. What does that mean? Because when I take the next row, I'm going to get some numbers. Well, I will continue with that thought. So sort of sometimes I don't quite know what I mean by this, but I feel as though I don't really care what these numbers are. By which I mean, if I replace these numbers by permutation of these numbers, if I'd said 23, 94, 176, 177, and a million, I would still have got 1, 1, 1, 1, 1 down here. So what I'm going to say is, supposing I have n numbers, and B1 of them are the same, and B2 of them are the same, and BR of them are the same. So this is, I've written this. What I mean is that I've got n numbers, and they might, and of those numbers, I've got sort of B1 A1s, B2 A2s, and up to BR ARs. So I should be able to write down what the next row is going to be if that's the case. And indeed I can. I'll have that's interesting. So it looks as though B1 is going to happen B1 times. B2 is going to happen B2 times. And so on up to BR is going to happen BR times. But that doesn't quite finish it because some of those numbers will be the same. So the next time round, my numbers. Okay, so let me just write that. I haven't got a very good notation for that. So B1 times, B2 times, BR times. But if BI equals BJ, then in fact I've got BI plus BJ times. So from this thing here, so even if the original numbers were, there were B1 A1s and B2 A2s up to BR ARs, and A1 and up to AR were all completely distinct. Once I've produced the next row, some of the numbers that were distinct cease to be distinct. But the only effect of that is going to be to merge some of these classes. So the number of distinct numbers is going to go down each time, or at least remain the same. And if it remains the same once, it's going to remain the same from then on. So that problem is done. I feel I haven't written down a very coherent solution to it, but I've definitely solved it. I've definitely seen that the invariant that matters is the number of distinct numbers. And let's just have a quick look at an example. So 1, 1, 2, 2, 3, 3, 3, 4, or something like that. Next time round, that's going to become 2, 2, 2, 2, 3, 3, 3, 1. And now we see a merger taking place. And so we get 4, 4, 4, 4, 3, 3, 3, 1. And now there are no more mergers to take place. So we're stuck at 4, 4, 4, 4, 3, 3, 3, 1. In fact, I could have maybe, I think this is an example actually where a bit more play and a bit less thought would have got there more quickly. So I went from looking at one example to just trying to describe in the abstract what goes on. Had I written down this example, I would have just seen really quite easily what was going on, and would perhaps have spared myself this abstract discussion. So it's a sort of interesting strategic decision to make in these situations. Okay, I think that's enough questions for one video. I will stop that and still plan to continue with this series, but that's it for today.